welcome to another pre-recorded video on the problem solving to aid you in your understanding of the concept. So our problem tells us that we have a point of a needle on a sewing machine. It moves in simple harmonic along the x-axis. It has a frequency of 2.5 hertz, and then at t is equal to 0, meaning at the initial time, its position and velocity components are at plus 1.1 centimeters, and its velocity component is negative 15 centimeters per second. So our task here is to find, we are asked to find for the acceleration component of the needle at t is equal to 0, meaning its initial acceleration component, and you are asked also in part B to write the equation that gives the position, velocity, and acceleration components of the point as a function of time. So the first thing that we are going to do is, in every problem we are working with, we always start with writing the given. So the given that we have in the problem is we have 2.5 hertz, so that is our frequency. Frequency is 2.5 hertz. Another is we have x sub 0 or x naught at 1.1 cm. So the naught here, meaning the x sub 0, that means that it's the initial position. So the same goes with v naught, meaning the initial velocity, that is given to be negative 15 centimeters per seconds. Okay, so the same with our previous examples. So we should be working with SI. So it is our convention in our class to always work with SI. So let's simply convert 1.1 cm to SI, meaning in meters. So we have 1.1 centimeters. You multiply it by the conversion factor of 1 meter, and there is 100 centimeters. So simply centimeters would cancel out, and since you divide it by 100 with 2 zeros, so what it means is that your decimal place will move 2 places towards the left. So you have 1, 2, so that will give you 0.011 meters. Okay, now for the velocity, the same goes with the velocity. You need to convert it into SI. So you have negative 15 centimeters per second. So you don't have a problem with second because that is the SI unit of time. You have a problem with centimeters instead, so you work with that. So in 1 meter you have 100 centimeters. So what happens is that the centimeters would cancel out, and since you are dividing it by 100, so the original decimal place will be moved 2 places towards the right, towards the left. So you will get negative 0.15 meters per second. Okay, so these quantities x naught and v naught are already in SI. Now, I think we are ready to solve for the part A, which asks us of the acceleration of the needle at t is equal to 0. So this is what the problem asks us to do. Okay, so if you remember in our previous class, we have actually derived an expression for acceleration, and it's actually given by this expression here, that the acceleration in simple harmonic motion is just a negative omega squared multiplied by x, right? And you know also, it's always repeated in our class that omega is simply 2 pi f, okay? Or another form of omega is equal to the square root of k over m. So this time around you see two different expressions for omega, and it should be clear to you what you are going to use, since this expression, which I will encircle in green, this expression is useless in this case because you have a force constant K, which is usually referring to the force constant of the spring, right? So since we are not dealing with springs in this problem, so you cannot use this formulation for omega. Instead, you can use this one because this expression here doesn't have force constant K. Okay, so from that, you work with that. So you'll have acceleration is equal to the negative of omega squared. So omega is just 2 pi f, and you square everything and then multiply it by x. So acceleration then is equal to the negative of, when you distribute the square, so you have 4 pi squared f squared multiplied by x. So the next line of equation is simply you work with your calculator and input the values. So 4 pi squared, your frequency is given to be 2.5 hertz, so you put it here, 2.5. But I will put the unit in 1 per second because hertz is just 1 per second. So I intentionally do this to show how the units would fare in the end part of the equation. And then you have x. Your x here is referring to x naught because your problem asks you for the acceleration at t is equal to 0. Thus, you need to use x, which refers to time t is equal to 0. So that is x naught. Okay, so that will be in SI, so 0.011 meters. Okay, so let me just plug in these values to my calculator. So we have 4 pi squared multiplied by 2.5 squared, and then you have 0.011. So you should get, if you round it off to 2 decimal places, you should get approximately equal to 2.71. Oh, I forgot the negative. It should be negative. Okay, forgot to write the negative. So it should be approximately equal to, okay, marker, should be approximately equal to negative 2.71. And when you look at the units, so you will find out that the unit is meters per, and then what happens to this term, this will be second squared, so meters per second squared. So you see, that is why it's very important to always include the units, because it's one way of checking if you are actually doing or working with the correct formula, because it will tell you in how you end up with units. So for example, if you find that it's not meters per second squared, you just see meters per second, which is the unit for velocity or speed, then that tells you that there must be something wrong with the equation with which you are using. So, mo na importante na sulat gud ninyo always ang units. Okay? One way of checking that. So the next the next problem, part of the problem asks us to write the equation. To write the equation giving the position. So this is the position as a function of time. So we are asked for this equation. The velocity as a function of time, and then the acceleration as a function of time. And as I have said in the class, when you are asked to find for these equations, there will always be these 3 important variables you need to solve first. So these are, the first you need to find for the amplitude. The next is for omega, or the angular frequency, and phi, meaning your phase angle. Since all of these equations here, the position as a function of time, velocity as a function of time, and acceleration as a function of time, are expressed in terms of these 3 variables. So let's move to the next page. Okay, so yep, I think this is fine. So for example, the position versus time is actually a cosine of omega t plus phi. So that is the equation for position as a function of time. Now, how about velocity as a function of time? So we have shown in the class that the velocity as a function of time is simply taking the derivative of this position as a function of time. So when you take the derivative of that, it will give you this expression that the velocity as a function of time is given to be negative a omega and then the sine of omega t plus phi. Now for the same thing happened with acceleration as a function of time. So you take the derivative of the velocity as a function of time, so you have negative omega squared a cosine of omega t plus phi. So as I have said earlier, all of these equations as a function of time are actually expressed in terms of the three variables: amplitude, the omega, and then the phase angle phi. So that's why we need to solve that first. So I will put it here, solving for, I think the first that we should solve, because it's very easy to find, is the omega. So you know that omega is equal to 2 pi f. Okay, so as I've said, 2 pi, it has understandably um, has a unit of radian, which is not a true unit in this case, or radian is really not a true unit for that matter. So the frequency, if we go back to the previous problem, it is given to be 2.5 hertz. So I will put it like 2.51 per second. Okay, so you will have, if you work with your calculator and plug in the values, so that will give you 5 pi, and then the unit would be rad per second. So you see, the unit is telling you that you are actually doing it right, or you are manipulating the correct equation, because you arrive with rad per second, which is what you expect for angular frequency. So for the next is we need to find for the acceleration, amplitude A. So when you solve for amplitude A, so this is already what's this, derived in the class, so we are going to use that. So that is x naught, I'm hoping you remember this, plus the initial velocity in x squared divided by the omega squared. Okay, so the amplitude then, so it's very important, class, when you do this, the first omega should be correct, because if you plug in the value of omega here and you solve it incorrectly, so you will get amplitude to be a mistaken value. So that's why it's really a chain reaction of the mistakes that you will do. So that's why it's important always to start with correct values. So you take the square root, so x naught, we have seen that to be 0.011 meters squared. Initial velocity is at 0.15 meters per second, square that, and then omega squared, you have solved that to be 5 pi rad per second. Okay, so in my calculation, I always showed the units, because that's one way of um, finding whether you're actually working with the correct equations or you simply miss some parts. Okay, so you work with your calculator, you plug in these values, so 0.011 squared plus 0.15 squared divided by 5 pi, and that should be squared. Okay, so let me just, okay, so you should find uh, a value that is equal to, okay, 5 pi rad. This should find value. Okay, my calculator gives me this value, 0.240. For the class, we are going to simply round to 2 decimal places, so you should get 0.02. Now when we deal with the units, so meter squared, this is meter squared. Okay, this is meter squared, so you can add that two terms because you have the same unit, so you don't have a problem with that. The second would cancel out, and you don't have any problem with rad because, as I have said, rad is not a true unit, so you can disregard that. So you have meter squared plus meter squared, so that means you can simply add that two units. So you add that, so you just have meter squared, and since understandably this is a square root, so the index is 2, so that would just cancel out, so you are left with meters, which is what you expect for amplitude. Okay, so it's going well. So we already found out omega, amplitude. So the last thing to solve in order to craft or to build our equations above is to solve for phi, for the phase angle phi. So we already have derived this in class. So we are going to use that formula in finding for the value of phi. Now, phi is just the tangent inverse of the absolute value of um, negative v naught x, since we are dealing with motion in x, divided by omega multiplied by x naught. Okay, so you simply plug in the value. We have the tangent inverse of negative v naught x is negative 0.15 meters per second. Divide everything by omega, which is 5 pi rad per second, and then you multiply it by x naught, or the initial position at t is equal to 0, and we found out that it's 0.011 meters. Okay, so the first thing that you should note when you will be working with tangent inverse, cosine inverse, um, sine inverse is that whatever the term that you're taking the tangent inverse of, or sine inverse or cosine inverse of, it should be dimensionless. So that means that you should the units should cancel out. Everything should cancel out. So let's check whether that will happen here. So meters, numerator, denominator, so cancel. Okay, second would cancel out. And rad, as I've said, is not a true unit, so you don't have any problem with that. So you see, it's now a dimensionless number. So this is what we expect if you solve for inverses. So you have the tangent inverse of this thing, you put it here and you do it in your calculator. So I will just directly do it with my calculator. So I have the tangent inverse of okay, everything that, so you will find out that it's giving you 0. When you round it up, 0.72 radian rad. Okay, so some of the important note here is that we are not working with degrees. We are actually working with radian measures here, so that is why your calculator should be in rad mode. Okay, it should be in rad mode, not degrees, because you will get a different answer if you have degrees here. Okay, so we are now ready to form these three equations, is because we already have omega, amplitude, and phi. So let's move to the next page to form this equation. So I'll find a better color, so I'll go with this one. Okay, so yeah, let's start. So for the position, it's so big. Let me just resize that. Okay, so for position as a function of time, you have seen that that is given by a omega cosine of omega t plus phi. So what you are going to do here is pretty straightforward. You simply plug in the values of a, omega, and phi. So let me write it here. So amplitude is given to be how much did we solve? So, I forgot. So that was 0.02 meters. So 0.02 meters. Omega is 5 pi rad per second. And then our phi is 0.72 radians. So this is, as I've said, pretty straightforward. So what you're going to do is to simply plug in the values. So for A, you have 0.02 meters. For omega, you have 5 pi rad per second. And then you have the cosine function. So 5 pi rad per second times time plus 0.72 rad. So that's how you do it. So x is a function of time. Okay, so this is fine, but you actually have the choice of, if you want to simplify it further, you can combine these two or multiply that two, but I think it will just mess it up, so it's better if you stick to that. So for the velocity as a function of time, so you will have uh, negative a omega, and then you now have sine, since this is simply the derivative of the position as a function of time. Okay, so this is easy. You plug in the values. 0.02 meters times omega is 5 pi rad per second, and then the sine function, the sine of 5 pi rad per second times time plus 0.72 radians. So this is your velocity as a function of time. And for the last, you're going to find for the acceleration as a function of time. So okay, so the acceleration as a function of time, that is simply negative a omega squared, or omega squared a, whichever works for you, cosine of omega t plus phi. Okay, so you plug in those values, so you have negative 0.02 meters, and then you multiply it by 5 pi rad per second, square that, and then the cosine of omega t plus phi. So I accept answers such as this form, but it's up to you if you want to further simplify this by squaring the 5 pi rad per second term. But this is fine. So I think that would be all for this pre-recorded example, and we'll have more in the class, and probably some problems such as this one, or like this one, on your problem sets. So if you have questions, just email me on your questions or put it in the comment section below.